What if I told you that everything you know, your home, your city, even the stars above, exists in a universe that is not only expanding but doing so in ways that challenge everything we thought we understood? Picture this: galaxies rushing away from each other at unimaginable speeds, the very fabric of space stretching endlessly, and forces so mysterious that they defy even the sharpest scientific minds. Today, we embark on an astonishing journey to unveil 25 incredible facts about the expanding universe, secrets that will not only spark your curiosity, but might just change the way you see everything around you. From the enigmatic force of dark energy to the afterglow of the Big Bang, each revelation will pull you deeper into the endlessly fascinating story of our cosmos. So, if you're ready to explore a universe that refuses to sit still, let's dive into the heart of the greatest mystery of all, how it's all expanding beyond imagination. Now turning to our first astonishing fact, the universe is expanding faster than the speed of light. At first glance, this might sound impossible, as nothing within the universe can travel faster than light. But here's the twist: this rule applies to objects within space, not to the fabric of space itself. Imagine the universe as a giant balloon with galaxies resting on its surface. When you blow up the balloon, the space between these galaxies stretches and they move apart. In this scenario, it's not the galaxies themselves speeding away from one another, but the balloon representing space expanding. During the earliest moments of the universe, a period we call cosmic inflation, space expanded at a rate that far exceeded the speed of light. This burst of rapid expansion occurred in less than a fraction of a second after the Big Bang and shaped the structure of the cosmos as we see it today. What's truly mind-boggling is that even now, distant regions of the universe continue to recede from us at speeds greater than light due to the ongoing expansion of space itself. This phenomenon doesn't violate the laws of physics because it's not about objects traveling through space, it's about space itself growing. This groundbreaking idea reshapes how we think about distances, the scale of the universe, and even time. It challenges our imaginations and reminds us that in the realm of the universe, our everyday rules of understanding don't always apply. And as we continue to unlock the secrets of this incredible process, it opens the door to deeper questions about the nature of our existence. Now turning to the second fascinating fact, the discovery of the expanding universe by Edwin Hubble. Before his groundbreaking work, the idea of a dynamic, ever-changing universe was far from mainstream. Most scientists believed the cosmos to be static and unchanging. However, in the 1920s, Hubble made a revolutionary observation that would forever alter humanity's understanding of the universe. Using the powerful Hooker telescope at Mount Wilson Observatory, he studied distant galaxies and noticed something extraordinary. The light from these galaxies appeared stretched, shifting towards the red end of the spectrum. This phenomenon, known as redshift, indicated that the galaxies were moving away from us. Hubble not only observed this but also uncovered a pattern: the farther away a galaxy was, the faster it seemed to be receding. This relationship, now known as Hubble's law, provided direct evidence that the universe is expanding. Imagine this on a cosmic scale: galaxies scattered like dots on the surface of a balloon, moving apart as the balloon inflates. Hubble's findings were monumental, challenging the prevailing notion of a static universe and providing support for the Big Bang theory. This discovery wasn't just a triumph of observation. It reshaped the foundations of cosmology, sparking countless questions about the origins, evolution, and future of the universe. Edwin Hubble's work is a reminder of how a single observation can upend conventional thinking and open the door to new realms of knowledge, realms that continue to inspire and intrigue scientists to this day. And as we delve further into the mysteries of the cosmos, it's clear that his legacy endures, guiding our quest to understand the vast and expanding universe. Moving forward, let's uncover the third astonishing fact: the role of dark energy in the universe's expansion. Picture this: for much of human history, we believed that gravity, with its immense and unyielding pull, would gradually slow the expansion of the universe over time. However, in the late 20th century, something extraordinary came to light. Observations of distant exploding stars called supernova revealed a shocking truth: the universe isn't just expanding, it's expanding faster and faster. This groundbreaking discovery introduced us to the concept of dark energy, a mysterious and unseen force that appears to be driving this acceleration. Scientists estimate that dark energy makes up about 68% of the universe, a staggering majority that we still know so little about. To put it simply, it's as though there's an invisible energy embedded in the very fabric of space, pushing galaxies apart with increasing speed. Theories about dark energy vary, with some suggesting it could be a property of empty space itself, described as the cosmological constant, while others speculate it might be a dynamic entity changing over time. Despite its elusive nature, the existence of dark energy is crucial for understanding the universe's fate. Will it continue expanding forever, grow colder and emptier, or perhaps tear itself apart in a catastrophic event often called the Big Rip? The questions dark energy raises are as profound as they are perplexing, making it one of the greatest mysteries in physics today. It's a stark reminder of how much we have yet to learn and how the universe continues to challenge everything we think we know. As we unravel these cosmic enigmas, one thing is certain: dark energy holds the key to understanding not just our universe's present but also its ultimate destiny. Now turning to the fourth fascinating fact, let's explore Hubble's law and its profound implications for understanding the universe. In the early 20th century, astronomer Edwin Hubble made a groundbreaking discovery that forever changed our comprehension of the cosmos. He observed that galaxies farther away from us are moving away faster than those closer to us, a relationship now known as Hubble's law. This law can be summarized in a simple yet astonishing principle: the speed at which a galaxy recedes is directly proportional to its distance from us. Imagine a loaf of raisin bread baking in the oven where the raisins represent galaxies. As the dough expands, the raisins move farther apart from each other. The farther apart two raisins are, the faster they move away from each other. This analogy perfectly illustrates the concept behind Hubble's law, with space itself stretching and carrying galaxies along with it. Scientists use Hubble's law to calculate the so-called Hubble constant, a value representing the universe's rate of expansion. By measuring the redshift of galaxies, essentially how much their light has been stretched as they move away, astronomers can estimate their velocity. Combining this with their measured distance, we gain insight into the rate of expansion. Perhaps even more remarkable, Hubble's law allows us to trace back in time to estimate the age of the universe. By reversing the expansion mathematically, astronomers calculate that the universe must have begun around 13.8 billion years ago. This incredible law not only helps us map the scale of the cosmos, but also serves as a cornerstone for our understanding of the universe's origins and its ever-evolving nature. As we dig deeper into these cosmic revelations, it becomes clear how interconnected every discovery is, painting a grand and intricate picture of the universe's story so far. Moving forward, we arrive at the fifth astounding fact: the cosmic microwave background radiation, often referred to as the faint afterglow of the Big Bang. This remarkable phenomenon is like a time capsule, offering us a glimpse into the universe's infancy. Over 13 billion years ago, when the universe was just a few 100,000 years old, it was a searing hot, dense ocean of particles and radiation. As the universe expanded and cooled, it reached a critical point where light could finally travel freely through space, creating what we now observe as the cosmic microwave background radiation. This faint glow of energy permeates the entire cosmos and has been detected in every direction we look. Its discovery in the 1960s revolutionized cosmology, providing concrete evidence that the universe experienced a hot, dense beginning, a finding that strongly supports the Big Bang theory. But this radiation is not just a relic of the past, it is a treasure trove of information. By studying slight variations in its temperature and density, scientists can map the early structure of the universe, revealing regions where matter first began to gather, eventually forming galaxies and other cosmic structures. These fluctuations also help us understand the universe's composition, confirming that ordinary matter, and dark energy each play a role in shaping its evolution. Essentially, the cosmic microwave background radiation is a snapshot of the universe's birth, preserved and stretched by billions of years of expansion. It serves as both a milestone in our journey to understand the cosmos and a constant reminder of how far our exploration has come. As we continue to unravel these mysteries, each discovery builds upon the last, deepening our connection to this vast and extraordinary universe. Now turning to the sixth astounding fact, we delve into the Big Bang, the monumental event that marks the origin of the universe's expansion and serves as the cornerstone of modern cosmology. Over 13 billion years ago, the universe began as an unimaginably hot and dense singularity, a point where all matter, energy, space, and time were compressed into an infinitesimal state. In a fraction of a second, this singularity began to expand rapidly, setting the stage for everything we see today. During the first few moments, the universe experienced a period of exponential growth known as cosmic inflation, stretching space itself at speeds beyond comprehension. As it expanded and cooled, fundamental particles such as quarks and gluons emerged, eventually combining to form protons and neutrons. Within the first 3 minutes, these particles fused in a process called nucleosynthesis, creating the first atomic nuclei, primarily hydrogen and helium. For the next 380,000 years, the universe remained a searing hot plasma, preventing light from traveling freely. It was only after this period, when the temperature dropped sufficiently for electrons to combine with nuclei and form neutral atoms, that light could escape, giving birth to the cosmic microwave background radiation discussed earlier. This marked the universe's first major step toward the complex cosmic structures we observe today. The Big Bang not only initiated the expansion of space, but also established the physical laws that govern it. By tracing the early timeline of the universe, scientists have unraveled how these initial moments set in motion the formation of stars, galaxies, and clusters. The theory of the Big Bang is supported by a wealth of evidence, including the cosmic microwave background radiation, the abundance of light elements, and the redshift of distant galaxies. Together, these findings create a compelling picture of a universe that grew from simplicity to complexity, evolving into the vast, dynamic cosmos we continue to explore. Moving forward, let's explore the seventh astounding fact, which dives into the distinction between the observable universe and the entire universe, a topic that truly stretches the limits of our understanding. The observable universe refers to the region of space that we can see or detect, limited by the finite speed of light and the universe's age. Light from objects farther away than approximately 46 billion light-years hasn't had enough time to reach us since the universe began its expansion over 13 billion years ago. This creates a cosmic horizon beyond which lies the unknown. But here's the mind-bending part: the entire universe could be much larger than what we can observe, potentially infinite in scope. Due to the relentless expansion of space, there are regions so far away that their light may never reach us, no matter how much time passes. This means that what we see is only a fraction of the whole picture, like viewing the tip of an iceberg while the vast majority remains hidden beneath the water. The expansion of the universe further complicates this, as distant regions are being pushed away faster than the speed of light due to the stretching of space itself. This not only limits what we can observe, but also ensures that some galaxies we currently see will eventually slip beyond our horizon, disappearing from view forever. The interplay between the observable universe and the entire universe highlights the profound mystery of cosmic expansion. It reminds us that while our telescopes and instruments have made remarkable discoveries, they can only reveal a small portion of the grander reality that lies beyond the reach of light and time. Now turning to the eighth astounding fact, we delve into the groundbreaking discovery of the universe's accelerated expansion, a revelation that forever altered our understanding of cosmology. In 1998, two independent teams of scientists set out to study distant exploding stars known as Type Ia supernova. These cosmic beacons are often referred to as standard candles because their consistent brightness allows astronomers to measure distances across vast stretches of space with remarkable precision. The expectation at the time was that the universe's expansion, initiated by the Big Bang, would be slowing down due to the pull of gravity. Instead, what they found was astonishing. These supernovae appeared dimmer than expected, indicating they were farther away than anticipated. This was concrete evidence that the universe is not only expanding but doing so at an accelerating rate. This paradigm-shifting discovery implied the presence of a mysterious and unseen force now known as dark energy, which is driving this accelerated expansion. The implications of this finding were so profound that it earned the leaders of the two research teams the Nobel Prize in Physics in 2011. This pivotal moment in science reshaped our cosmic perspective, revealing that dark energy dominates the universe, accounting for roughly 68% of its total composition. It opened a new chapter in astrophysics, sparking countless questions about the nature of this enigmatic force. What is dark energy? How does it work? And what does it mean for the ultimate fate of the universe? These mysteries remain unsolved, underscoring how even the brightest discoveries often lead to deeper and more profound questions about the cosmos. Moving forward, let us explore the ninth astounding fact, which takes us into the intriguing question of the universe's shape and its connection to the rate of expansion. Cosmologists have theorized that the universe could take one of three possible shapes: flat, open, or closed. These shapes are not about the universe having edges or a physical boundary. They refer to the geometry of space itself. A flat universe, as the name suggests, means that space operates under the rules of Euclidean geometry. Parallel lines would stay parallel forever, and the angles of a triangle would add up to 180 degrees no matter where it is drawn. Observational evidence strongly supports this model, suggesting that the universe is flat on a large scale. An open universe, on the other hand, resembles a saddle shape, where parallel lines would diverge over long distances, and the angles of a triangle would sum to less than 180 degrees. Finally, a closed universe is like the surface of a sphere, where parallel lines converge eventually, and the angles of a triangle sum to more than 180 degrees. These different geometries are determined by the universe's total energy density, including all matter, radiation, and dark energy. If the density is just right, the critical density, the universe will be flat. If it is higher than the critical density, it will be closed, and if it is lower, it will be open. The rate of expansion plays a crucial role in shaping this geometry. Thanks to precise measurements of the cosmic microwave background radiation and other observational data, scientists believe the universe is flat and will continue expanding indefinitely. But as with all things in cosmology, the story is far from over. The universe's shape and expansion remain active fields of study, with new discoveries potentially altering our understanding of the cosmos. Now turning to the 10th astounding fact, let us unravel why the expansion of the universe does not affect bound systems like galaxies or solar systems. While the universe as a whole is expanding, the key lies in the interplay between gravity and this cosmic stretching. Gravity is an incredibly powerful force on smaller scales, and it keeps objects that are gravitationally bound together from being pulled apart by the universe's expansion. Imagine it this way: think of the universe's expansion as the stretching of a rubber sheet. Objects like galaxies or solar systems are held together by their own gravitational glue, which is far stronger than the force attempting to stretch them apart. This is why stars stay in orbit within galaxies, planets continue to circle stars, and you don't wake up every morning to find that the Earth has doubled in size. The fabric of space is indeed stretching, but within these bound systems, gravity completely overwhelms this effect. To put this in perspective, within galaxies and even clusters of galaxies, the gravitational forces are so dominant that they effectively override the larger scale expansion of the universe. This is why the Milky Way, Andromeda, and other galaxies in our local group are not getting farther apart. They are gravitationally bound to each other, which is why Andromeda is on a collision course with the Milky Way billions of years from now. This cosmic tug of war between gravity and expansion reveals just how intricate and finely balanced the forces of the universe truly are, providing a fascinating insight into why we observe the cosmos the way we do. Moving forward, let us delve into the next captivating fact, exploring the horizon problem and how the inflation theory offers a groundbreaking solution to this cosmic conundrum. With the next phase of the journey in sight, we arrive at the 11th astounding fact, the horizon problem and the ingenious theory of cosmic inflation that resolves it. The horizon problem is one of the most perplexing puzzles in cosmology. It arises from the observation that the universe, even in regions separated by vast distances, has nearly the same temperature. For example, the cosmic microwave background, often referred to as the afterglow of the Big Bang, exhibits almost uniform temperature no matter where we look. Here is the dilemma. These vastly separated regions should not have been able to exchange any information or energy, given the finite speed of light and the age of the universe. So, how do these distant parts of the universe exhibit such remarkable thermal equilibrium? This question baffled scientists for decades. Enter the inflation theory, a groundbreaking idea that not only resolves this mystery but also reshapes our understanding of the early universe. Inflation posits that just a fraction of a second after the Big Bang, the universe underwent an unimaginably rapid expansion, growing exponentially in size at speeds far greater than the speed of light. During this brief but dramatic period, the entire observable universe was incredibly small and tightly connected, allowing energy and information to smooth out any differences in temperature. When inflation ended, the universe continued to expand at a slower rate, preserving this uniformity across vast distances. In essence, inflation acts as the great cosmic equalizer, explaining why the universe appears so uniform on the largest scales. It is like stretching a small, smooth balloon to create a massive sphere. The smoothness of the original surface remains, no matter how large the balloon becomes. This elegant solution not only addresses the horizon problem, but also sets the stage for deeper investigations into the mysteries of our cosmos. And as we continue, let us delve into the next astonishing fact about the expanding universe, where we explore how redshift serves as key evidence for this cosmic expansion. Now turning to the 12th astounding fact, we unravel the concept of redshift and why it stands as key evidence for the expansion of the universe. Imagine the sound of a passing train. As it approaches, the sound waves compress, creating a higher-pitched tone, and as it moves away, the sound waves stretch, resulting in a lower pitch. This familiar phenomenon is known as the Doppler effect, and it applies not only to sound but also to light. When light travels from an object moving away from us, its waves stretch, shifting toward the red end of the spectrum. This is what astronomers call redshift. By observing the light from distant galaxies, scientists have noticed a consistent pattern. The farther a galaxy is from Earth, the more its light is redshifted. This means that these galaxies are moving away at faster speeds, a discovery that forms the backbone of Hubble's law, which we explored earlier. Redshift, therefore, serves as a kind of cosmic fingerprint, allowing astronomers to measure not only how fast a galaxy is moving away from us, but also how far away it is. It is through this technique that we have mapped the vast expanse of the cosmos and confirmed that the universe is not static but expanding. In essence, redshift gives us a glimpse into the dynamic and evolving nature of the universe, like reading an ancient scroll that unfolds the story of cosmic history. Remarkably, this simple yet profound principle allows us to bridge the immense distances of space and time, connecting our understanding of the universe's past, present, and future. And now, as we move forward, we dive into the next astonishing fact about the expanding universe, where we confront the mind-bending idea that the universe is not expanding into anything at all. Now turning to the 13th astounding fact, we delve into the perplexing question of what exactly the universe is expanding into. At first glance, it seems natural to assume that the universe must be stretching into some kind of pre-existing space, like a balloon inflating into the air around it. But here is where reality takes a mind-bending turn. The universe is not expanding into anything. Instead, it is creating more space as it grows. To understand this, imagine drawing dots on the surface of a balloon. As you blow it up, the surface stretches and the dots move farther apart, but crucially, the surface itself is all there is. There is no inside or outside on the two-dimensional plane of the balloon. Similarly, the expansion of the universe is not about galaxies moving outward into empty space, but rather about the very fabric of space itself swelling everywhere. This means there is no edge to the universe as we know it and no outside for it to expand into. The creation of new space happens uniformly, stretching the distances between galaxies without requiring a physical boundary. This concept challenges our intuitive understanding of space and leaves us grappling with the profound idea that the universe is a self-contained entity. It grows not by filling a larger container, but by continuously generating the container itself. As strange as this seems, it is supported by the mathematical framework of modern cosmology. It redefines our sense of scale and forces us to contemplate a cosmos without edges, one that unfolds infinitely in all directions yet is finite in what we can observe. And with this astonishing perspective in mind, we now venture to the next fact, where we explore how gravity plays a crucial role in shaping the universe's vast structure despite its relentless expansion. Now turning to the 14th astounding fact, we uncover the pivotal role of gravity in the grand cosmic tug-of-war that shapes the universe. While the universe as a whole continues to expand at an accelerating pace, gravity works as a counterforce, reigning in the chaos on smaller scales. Picture this: galaxies, solar systems, and even clusters of galaxies are held together by the relentless pull of gravity, preventing them from being swept apart by the expansion of space. These bound systems exist as islands of stability in a sea of ever-growing distances, but gravity does not act alone. It competes with the driving force of expansion. On small scales, like within our Milky Way galaxy or even our own solar system, gravity is strong enough to dominate, holding everything firmly in place. However, on a much larger scale, where the distances between objects such as galaxy superclusters stretch into the billions of light years, gravity's grip weakens. Here, the accelerating expansion powered by dark energy takes over, pushing these colossal structures farther apart. This cosmic balance between gravity and expansion is essential to the universe's vast web-like structure. Without gravity's counteracting influence, galaxies would not form, and the universe as we know it would be a featureless void. This ongoing interplay has profound implications, influencing not just how the universe evolves, but also how we understand the forces that govern it. As we reflect on gravity's vital role in binding the cosmos together, let us move forward to explore how this never-ending expansion might influence the ultimate fate of the universe. Moving forward to the 15th astounding fact, we delve into the profound ways the universe's expansion could dictate its ultimate fate. Scientists have long theorized three major scenarios that could define the cosmos's destiny, each hinging on the interplay between the forces of expansion and gravity. The first possibility is what is known as the Big Crunch. In this scenario, if gravity were to eventually overpower the accelerating expansion, the universe might reverse course, gradually contracting until all matter and energy collapse into an unimaginably dense point. This would essentially bring the universe back to a state similar to its beginning, an end that mirrors its fiery birth in the Big Bang. On the other hand, the second scenario paints a very different picture, the Big Freeze. Here, the expansion continues indefinitely, driven by dark energy, causing galaxies and stars to drift farther apart over billions of years. As distances grow, stars will burn out and galaxies will dim, leaving a cold, dark, and lifeless universe, a fate where time stretches endlessly but activity nearly ceases. The third and perhaps most dramatic possibility is the Big Rip. This scenario envisions a future where the acceleration of expansion becomes so extreme that it tears apart the very fabric of the cosmos. Not just galaxies and stars, but even atoms and subatomic particles could be ripped asunder, leaving behind a void of chaos and destruction. These competing theories remind us that the ultimate fate of the universe rests on forces we are only beginning to understand. As we venture deeper into the mysteries of cosmic expansion, one thing is clear. Whether the universe collapses, freezes, or rends itself apart, its destiny is as awe-inspiring as its origins. With the next phase of the journey in sight, let us explore the 16th astounding fact. The observable universe is growing larger with each passing second. At first glance, this might seem contradictory after all. How can we observe more of the universe if everything is moving farther apart? The answer lies in the nature of light and the speed of its travel. Light from distant galaxies takes billions of years to reach us, meaning that when we look into the night sky, we are essentially peering into the past. As space expands, light from regions previously beyond our view is stretched into our observable range, revealing new cosmic territories that were once hidden. This means that the boundary of the observable universe, what we can detect with telescopes, continues to grow outward, adding to the vastness of what we can study. But there is a bittersweet twist to this phenomenon. While new regions become visible, others are slipping beyond our reach. The accelerated expansion of the universe is pushing some galaxies so far away that their light will never reach us again. Over time, these galaxies will fade from view, vanishing into the cosmic darkness. This dual reality of gaining and losing sight underscores the transient nature of what we can observe. It also serves as a humbling reminder of the sheer magnitude and complexity of the universe, where expansion not only shapes our understanding but also defines the limits of our cosmic vision. And yet, as we continue to explore, the mysteries of what lies beyond remain as compelling as ever. Moving forward, let us uncover the 17th intriguing fact, the peculiar motion of galaxies. While the universe's expansion drives galaxies apart, their individual movements, shaped by local gravitational influences, add an extra layer of complexity to the cosmic dance. This results in what astronomers call peculiar velocity, a term that describes the unique directional movement of galaxies relative to the overall expansion. Imagine a bustling train station where the trains are all departing from a central hub, but each one navigates its own distinct path as it encounters various obstacles and turns along the way. In a similar manner, galaxies do not simply drift smoothly outward. Instead, they interact with one another through gravitational forces, causing them to sway, cluster, or even collide. For example, our own Milky Way galaxy and its neighbor, the Andromeda Galaxy, are currently on a collision course despite the universe expanding around them. This might sound chaotic, but these interactions are crucial to forming the large-scale structures we see in the universe, such as galaxy clusters and superclusters. On smaller scales, this peculiar motion can make it seem as though galaxies are moving unpredictably, but when viewed on the grander cosmic scale, it becomes clear that their movement is intricately coordinated by the twin forces of gravity and expansion. Studying these peculiar velocities helps astronomers understand not only the interactions between galaxies, but also the unseen influences of dark matter shaping their paths. This fascinating interplay of forces reveals a level of complexity that adds to the wonder of the expanding universe, a dynamic and ever-changing backdrop to the story of cosmic evolution. With the next phase of the journey in sight, let us explore the 18th astounding fact, the multiverse hypothesis and its connection to the expanding universe. Imagine for a moment that our universe, vast and infinite as it seems, might just be one of countless others. This mind-bending idea stems from a concept known as eternal inflation, which suggests that the rapid expansion that occurred immediately after the Big Bang may not have been a one-time event. Instead, it could be continuously happening in isolated pockets of a much larger cosmos, creating entirely new universes in the process. Picture an endless pot of boiling water, where each bubble represents a separate universe forming and expanding on its own. These bubbles could have entirely different properties from our own universe, such as different laws of physics, dimensions, or even forms of matter and energy. While the multiverse hypothesis remains speculative and unproven, it offers an intriguing framework for understanding the scale of existence in its entirety. Expansion here takes on a whole new meaning, not just the stretching of our own universe, but the possibility that this process is occurring endlessly across a far greater reality. This challenges our very perception of space, time, and our place within it. If true, the multiverse concept might hold answers to some of the most profound questions about why the universe is the way it is or why it exists at all. While we have yet to gather direct evidence of these other universes, the mathematical models and theories supporting eternal inflation continue to inspire scientists to search for clues. Could the expanding universe we observe be just one chapter in an infinite library of cosmic creations? As we ponder this possibility, one thing becomes clear. The more we uncover about the nature of expansion, the more it reveals how much we have yet to understand. Moving forward, let us unravel the 19th astounding fact, the role of dark matter in shaping the structure of the universe. While dark matter might not directly contribute to the expansion of the universe, it is absolutely essential for maintaining and molding its vast and intricate framework. Dark matter is a mysterious and invisible substance that does not emit, absorb, or reflect light, making it impossible to observe directly. However, its presence is inferred from the gravitational effects it has on visible matter, such as stars, galaxies, and galaxy clusters. Without dark matter, the universe as we know it would look dramatically different. Imagine a cosmos in which galaxies could not even form because there would be nothing to hold them together. Dark matter acts like an unseen cosmic scaffolding, creating the gravitational wells that allow galaxies to coalesce and remain stable over billions of years. It is estimated to make up about 85% of the total matter in the universe, far outweighing the small fraction of visible matter composed of stars, planets, and gas. This unseen mass plays a pivotal role in the formation of large-scale structures, such as galaxy clusters and superclusters, as well as the vast cosmic web that connects them. Through computer simulations and observations of how galaxies and other celestial objects move, scientists have mapped out this invisible framework, revealing a universe that looks almost like a vast network of filaments and nodes. These patterns are shaped and sustained by the gravitational pull of dark matter, without which the universe would lack the order and cohesion we see today. While much remains unknown about its true nature, dark matter highlights the profound interconnectedness of the cosmos and reminds us that much of the universe's story is written in what we cannot see. Its role in shaping the expanding universe underscores how even the unseen elements of reality can have monumental impacts on the grand cosmic design. As we contemplate the enigmatic force of dark matter, we are led to wonder, what other secrets does it hold waiting to be uncovered? With the next phase of the journey in sight, let us delve into the 20th astounding fact, how the expansion rate of the universe has changed over time. In its early stages, shortly after the Big Bang, the universe experienced a phase of rapid inflation. This was a brief but extraordinary period when the cosmos expanded exponentially in less than a fraction of a second. Following this dramatic burst, the expansion slowed down significantly as the gravitational pull of matter began to counteract the initial momentum. During this phase, the universe's growth was largely dictated by the density of matter and the gravitational interactions within it. Over billions of years, this tug-of-war between momentum and gravity shaped the large-scale structures we observe in the universe today. However, something remarkable happened approximately 5 billion years ago. Scientists discovered that the expansion of the cosmos began to speed up again, an observation that took the scientific community by storm. This accelerated expansion is attributed to a mysterious force known as dark energy, which we touched upon earlier in this journey. While its true nature remains enigmatic, dark energy seems to act as a kind of anti-gravity, pushing galaxies apart at an ever-increasing rate. This dramatic shift marked a turning point in the universe's story, signifying that dark energy now dominates over gravity on cosmic scales. The interplay between these competing forces not only reveals the dynamic nature of our universe, but also raises profound questions about its ultimate fate. Will dark energy continue to accelerate expansion indefinitely, or could some future discovery alter our understanding of how the universe evolves? As we explore these mysteries, we are reminded that the history of the cosmos is one of constant transformation, dictated by forces both seen and unseen. What lies ahead remains one of the most fascinating uncertainties in the realm of astrophysics, driving our curiosity to new heights. Now turning to the 21st astounding fact, let us explore the fascinating role of gravitational waves as tools for uncovering the universe's expansion history. Gravitational waves are often described as ripples in space-time, created by some of the most violent and energetic events in the cosmos. When massive objects like black holes or neutron stars collide, they send out these ripples, traveling across the universe at the speed of light. But how do these waves help us understand the expanding universe? Here's where things get truly intriguing. As gravitational waves journey through space, they carry within them the imprints of the universe's structure and expansion at the time they were launched. By analyzing these ripples, scientists can essentially peer into the past, measuring the rate at which space itself was stretching billions of years ago. This gives us valuable clues about how the expansion of the universe has changed over time. What makes gravitational waves unique is that they allow astronomers to study phenomena that are otherwise invisible with traditional methods like observing light. For example, when a gravitational wave from a distant collision reaches Earth, it distorts space-time ever so slightly, and highly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory can detect these changes. By precisely measuring the properties of the wave, scientists can determine how far away the event occurred and gain insights into the cosmic conditions of that era. This has opened a groundbreaking new window into astrophysics, offering a way to independently verify and refine measurements of the universe's expansion rate, such as those derived from the movement of galaxies. However, this field of research is still in its infancy, with much to learn as technology advances and more gravitational wave events are observed. Even so, the insights gained so far demonstrate the incredible promise of this method, sparking excitement about its potential to resolve some of the biggest questions in cosmology. As we harness the whispers of the universe carried by these waves, we venture closer to unraveling the mysteries of its vast and ever-changing story. Moving forward, let us delve into the 22nd astounding fact about the expanding universe, the creation of cosmic voids. As galaxies and galaxy superclusters are carried along by the relentless expansion of the universe, something remarkable happens on the grandest scales. Vast regions of space emerge that are almost completely empty, known as cosmic voids. These voids are not just random gaps, but are structured in a way that forms a web-like pattern across the cosmos, often referred to as the cosmic web. At the intersections of this web lie dense clusters of galaxies and superclusters, while the spaces in between grow into enormous voids as the universe expands. The formation of these voids is a direct consequence of the way matter clumps together under the influence of gravity. Over billions of years, areas with slightly higher densities of matter have drawn in more material from their surroundings, forming the dense regions we recognize as galaxies and clusters. Meanwhile, the less dense areas have been emptied out, creating these enormous voids that span hundreds of millions of light-years across. The result is a universe that resembles a sponge or foam, where the bulk of matter is concentrated along thin filaments, and the spaces in between are vast, dark voids. These cosmic voids are fascinating not just because of their scale, but also because they offer unique opportunities for scientific study. By analyzing the distribution and properties of these voids, astronomers can gain insights into the rate of the universe's expansion and the nature of the mysterious forces driving it, such as dark energy. Interestingly, these voids are also quieter regions of the universe, free from the intense gravitational interactions found in denser areas. This makes them ideal laboratories for testing fundamental physics, as they are less influenced by complex interactions. The existence of cosmic voids underscores the profound impact of expansion on the large-scale structure of the universe, revealing a cosmos that is not uniform but intricately textured. As we continue to map these vast empty spaces, we uncover more about the dynamic processes that have shaped the universe into the extraordinary tapestry we see today. Now turning to the 23rd astounding fact about the expanding universe, we explore the connection between the universe's age and the ongoing debate surrounding the Hubble constant. The Hubble constant is a critical value that represents the rate of the universe's expansion. By understanding how fast the universe is expanding, scientists can work backward to estimate its age, a calculation that has monumental implications for our understanding of cosmic history. Current estimates place the age of the universe at approximately 13,800,000,000 years. However, calculating this age relies heavily on accurately determining the Hubble constant, and this is where the controversy begins. Different methods of measuring this rate have led to slightly different results, sparking one of the most intriguing debates in modern cosmology. On one hand, measurements based on observations of the cosmic microwave background radiation, the faint glow left over from the Big Bang, tend to produce a lower value for the Hubble constant. On the other hand, observations of distant supernovae, which act as cosmic mileposts, often suggest a higher value. The discrepancy between these measurements is small but significant, as it directly impacts our understanding of how the universe has evolved since its beginning. This divide has led to questions about whether there might be unknown factors influencing the universe's expansion that we have yet to uncover. Some theories propose that this discrepancy could point to entirely new physics beyond our current understanding, while others suggest it may simply result from differences in the methods or data used. Resolving this controversy is a top priority for astronomers, as it holds the key to refining our models of the cosmos and understanding the interplay of forces like dark energy and gravity. What makes this debate particularly fascinating is that it reminds us of how much we still have to learn. Even with all the tools and knowledge at our disposal, the universe continues to surprise and challenge us. As researchers work to reconcile these differences, new observations and technologies may eventually reveal the truth, shedding light on this complex and deeply important question. The Hubble constant controversy underscores the evolving nature of science and invites us to remain curious about the mysteries that define our existence. Moving forward, let us examine the 24th astounding fact about the expanding universe, diving into the fascinating role of quantum fluctuations during the era of inflation. To understand this, we must revisit a fraction of a second after the Big Bang, a time when the universe underwent an extraordinary burst of rapid expansion known as cosmic inflation. During this incredibly brief period, the universe expanded exponentially, stretching from a subatomic scale to macroscopic dimensions in what feels like the blink of an eye. Within this phase of inflation, tiny, random variations in energy levels known as quantum fluctuations appeared. These fluctuations were unimaginably small, existing on scales far beyond the reach of even our most advanced microscopes. However, as inflation stretched the fabric of space, these quantum fluctuations expanded as well, growing from microscopic irregularities to the seeds of the vast structures we observe today. Over billions of years, the gravitational pull of these slight variations caused matter to clump together, forming the galaxies, stars, and clusters that shape the cosmic web spanning across the universe. Without these early quantum fluctuations, the universe might have remained an empty expanse, devoid of the beautiful structures we see when we gaze at the night sky. What is truly remarkable is that these initial fluctuations, rooted in the strange and unpredictable world of quantum mechanics, have grown to define the large-scale architecture of the universe, bridging the smallest and largest scales known to science. This discovery reminds us of the profound interconnectedness of cosmology and quantum physics, showing how principles governing the tiniest particles can influence the universe's grandest structures. As scientists continue to explore the mysteries of inflation and quantum mechanics, new insights may further illuminate how these foundational processes shape the cosmos we call home. With the next phase of the journey in sight, let us delve into the 25th astounding fact about the expanding universe, the ongoing debate over whether its expansion could be infinite or finite. This question lies at the heart of modern cosmology, touching on the ultimate fate of the universe and the laws that govern it. Currently, scientists consider three primary scenarios for this cosmic expansion. In the first scenario, the universe could expand forever, driven by the mysterious force of dark energy. If dark energy's influence persists, it may outpace gravity's ability to pull matter back together, leading to what is often called the Big Freeze. Over unimaginably long timescales, galaxies would drift apart, stars would burn out, and the cosmos would become a cold, dark void. The second possibility is a finite expansion, where the influence of gravity eventually overtakes dark energy. In this case, the universe might slow its expansion, stop, and then reverse, culminating in what astronomers call the Big Crunch. In this dramatic ending, all matter would collapse into a dense, hot state, potentially leading to conditions similar to those of the Big Bang. The third and perhaps most mysterious scenario is the Big Rip, in which dark energy grows stronger over time, tearing galaxies, stars, planets, and even atoms apart as the expansion accelerates without bounds. Each of these possibilities depends heavily on the true nature and behavior of dark energy, a force we currently understand only partially. What adds even more intrigue is the idea that the universe could transition into unknown phenomena beyond these scenarios, or that its expansion could reveal entirely new laws of physics. As our observational tools and theoretical models improve, we may uncover clues that point toward one of these fates or perhaps a new, unimagined destiny. This ongoing exploration highlights not only our curiosity about the cosmos, but also humanity's relentless drive to understand our place within it. And while the final answer may yet elude us, the journey to uncover it has already transformed our understanding of the universe and will continue to inspire awe for generations to come. With the next phase of the journey in sight, let us contemplate the profound philosophical implications of an ever-expanding universe. The sheer vastness and dynamic nature of the cosmos challenge our understanding of existence and compel us to rethink humanity's place within this grand, ever-changing tapestry. As we observe galaxies racing away and vast voids growing larger, we are reminded of the humbling reality that our planet, our solar system, and even our galaxy occupy but a minuscule corner of the vast cosmic expanse. This raises an age-old question: what is our significance in a universe that seems almost indifferent to our existence? Some may find this thought disheartening, but for many it sparks a sense of wonder. The universe's expansion reveals a cosmos filled with mysteries waiting to be uncovered, an infinite playground for human curiosity and innovation. It also forces us to confront the limits of human knowledge. How much of this immeasurable expanse can we truly understand? If the universe is infinite, does that mean the possibilities for discovery are infinite as well? Or do we inevitably face boundaries to what our species can comprehend? These questions have deep implications not just for science, but also for human philosophy and spirituality. They challenge us to explore what it means to exist in a universe that evolves on scales so vast they defy our everyday perception of time and space. They demand that we consider how our transient lives fit into this larger narrative. Perhaps the most awe-inspiring aspect of an expanding universe is how it unites us in our shared quest for understanding. Regardless of culture, language, or belief, every human being gazes upon the same stars, peers at the same galaxies, and marvels at the same unfolding story of existence. This shared curiosity reminds us that while the universe is vast and seemingly boundless, it has the power to connect us in our search for meaning. The expansion of the universe is not just a scientific phenomenon, but a catalyst for introspection and wonder. It invites us to think deeply about who we are, where we come from, and where we might be headed, both as individuals and as a species. And as we continue to uncover the secrets of the cosmos, we are reminded that the journey itself, the ceaseless pursuit of knowledge, might just be the most profound answer to the questions we seek. Now turning to the first moments after the Big Bang, let us journey back to the very beginning of time and space as we know it. Roughly 13,800,000,000 years ago, the universe sprang into existence in an unimaginably hot and dense state. In the first fraction of a second, an era known as cosmic inflation occurred, during which the universe expanded exponentially, growing from a size smaller than an atom to a scale incomprehensibly vast. This rapid expansion laid the groundwork for the structure of the cosmos, stretching and smoothing out the fabric of space itself. As the inflationary period ended, the universe entered what is known as the quark-gluon plasma phase. During this time, extreme temperatures and densities allowed only the tiniest building blocks of matter quarks and gluons to exist freely, a chaotic dance of particles without form or structure. But as the universe continued to expand, it began to cool. Within just a few microseconds, quarks started combining to form protons and neutrons, the building blocks of atomic nuclei. By the time the universe was just a few minutes old, a process called primordial nucleosynthesis began. This was when the first simple nuclei of hydrogen, helium, and trace amounts of lithium were forged. These primordial elements remain the most abundant in the universe to this day. Over the next 380,000 years, the universe continued to expand and cool, eventually reaching a temperature at which electrons could combine with atomic nuclei to form neutral atoms. This process, known as recombination, allowed light to finally travel freely through space, creating the cosmic microwave background radiation, a faint glow still detectable today and a critical piece of evidence for the Big Bang. These first moments after the Big Bang were not only a time of immense transformation, but also the foundation for everything we observe in the universe today. From the galaxies and stars to the very atoms in our bodies, every piece of matter can trace its origins back to these early phases of expansion. Such is the incredible story written in the light of the cosmos, a reminder that even in the apparent chaos of creation, the seeds of order, complexity, and life itself were sown. Moving forward, let us dive into the fascinating world of technology that has enabled us to uncover the accelerating expansion of the universe. Observations of distant supernova, particularly the type known as Type 1a, played a pivotal role in this groundbreaking discovery. But capturing the light from these stellar explosions, which occurred billions of years ago, requires instruments of extraordinary precision and capability. At the forefront of this endeavor are space-based telescopes like the Hubble Space Telescope. Positioned above Earth's atmosphere, these telescopes provide a clear and unobstructed view of the universe, allowing astronomers to detect even the faintest and most distant supernova. Ground-based telescopes equipped with adaptive optics systems are also key players. These systems counteract the distortions caused by Earth's atmosphere, sharpening the focus of images captured from the ground. In addition, advanced spectrographs are used to analyze the light from supernova, breaking it down into its component wavelengths. This reveals critical information about a supernova's distance and the rate at which its host galaxy is receding from us. The development of large-scale surveys like the Sloan Digital Sky Survey has further revolutionized this field. These surveys systematically search vast regions of the sky, increasing the chances of finding these rare cosmic events. With the help of automated algorithms, astronomers can quickly identify and study potential supernova candidates. The groundbreaking discovery of the accelerating universe in 1998, which won the Nobel Prize, hinged on these technological advancements. Without the precise data provided by these sophisticated tools, the realization that dark energy is driving the universe's expansion would have remained hidden. These technologies not only deepen our understanding of cosmic acceleration, but also open the door to uncovering even more profound cosmic mysteries. Now turning to the intriguing topic of the Hubble constant discrepancy, we find ourselves at the crossroads of science and philosophy, where questions about the universe's very fabric unfold. The Hubble constant, which measures the rate at which the universe is expanding, has long been a cornerstone in cosmology. However, recent years have revealed a perplexing tension in its value depending on the method used for measurement. When astronomers measure the Hubble constant using observations of the early universe, such as the cosmic microwave background radiation detected by the Planck satellite, they arrive at one value. Yet, when the constant is derived using measurements of the more recent universe, such as through the distances and redshifts of supernova or Cepheid variables, a distinctly different value emerges. This discrepancy has sparked intense debate and may suggest that our current model of the universe, known as the Standard Model of Cosmology, is incomplete. If these differing values cannot be reconciled, it could imply the existence of unknown physics at play, perhaps a new form of energy, unknown particles, or even a deeper modification to our understanding of gravity. Beyond the realm of science, this puzzle also encourages us to reflect on the profound limitations of human knowledge. It highlights how each discovery not only brings answers but also reveals new layers of mystery, urging us to continually question and refine our understanding of the cosmos. As scientists work tirelessly to resolve this enigma, one thing becomes clear: the universe is far more complex and astonishing than we ever imagined. Moving forward, let's unravel an intriguing paradox about the universe: how galaxies manage to cluster together and form superclusters despite the relentless expansion of space. At first glance, it might seem logical that as the universe expands, every galaxy would drift farther apart, isolated in an ever-growing void. However, the reality is more nuanced. While the large-scale expansion of the universe pushes galaxies away from each other, gravitational forces on smaller scales paint a different picture. Gravity, the invisible force that binds celestial objects together, plays a dominant role in shaping the cosmos on localized levels. Within a galaxy, stars remain bound together due to their gravitational attraction, as do the components of a solar system like planets and moons. But gravity does not stop there. It also acts across much greater distances, pulling galaxies together into groups, clusters, and even larger structures known as superclusters. These immense assemblies are some of the largest structures in the universe, containing thousands of galaxies held together by their mutual gravitational pull. In these areas, the force of gravity overpowers the outward push of cosmic expansion. Imagine it like the tension between a balloon being inflated and small weights attached to its surface. While the balloon expands, the weights can remain close together due to their mutual pull. The result is a universe that is both expanding and intricately connected on smaller scales. This intricate balance between gravitational attraction and the universe's overall expansion shapes the cosmic web we observe today. It demonstrates how the interplay of forces creates a universe that is both dynamic and structured, where galaxies are not just scattered randomly but grouped into patterns that tell a story of cosmic evolution. This fascinating duality reminds us that the forces shaping our universe are as complex as they are beautiful. Now, let us explore another compelling twist in the tale of our expanding cosmos. Now turning to one of the most profound mysteries of modern cosmology, the enigmatic force we call dark energy. Despite accounting for nearly 70% of the universe, dark energy remains one of the most elusive phenomena in science. But what exactly is it? While we do not know its precise nature, scientists have developed several compelling theories to explain its role in driving the accelerated expansion of the universe. One idea revolves around the cosmological constant, originally introduced by Albert Einstein over a century ago. Einstein initially proposed this concept as a mathematical term to balance his equations, believing at the time that the universe was static. Later, when it was discovered that the universe is expanding, Einstein famously dismissed the cosmological constant as his greatest blunder. However, the concept was resurrected in modern cosmology when astronomers realized the universe's expansion is not just continuing but accelerating. The cosmological constant suggests that the energy of empty space itself, what some call the energy of the vacuum, could exert a repulsive force, counteracting gravity on the largest scales and speeding up expansion. Another intriguing possibility is something known as quintessence. Unlike the cosmological constant, which implies a static, unchanging energy of space, quintessence suggests that dark energy could evolve over time. This hypothetical energy field would have properties that shift as the universe ages, leading to variations in the rate of expansion. Quintessence offers a more dynamic view of dark energy, one that changes with the universe's history. Finally, there is the idea of vacuum energy, which ties to the strange principles of quantum mechanics. In this view, even empty space is not truly empty, but teems with tiny fluctuations of energy at a quantum level. These fluctuations could give rise to the cosmic push we attribute to dark energy, though precise measurements are still beyond our reach. Each of these theories opens new doors to understanding the universe, but also raises profound questions about the nature of reality. Is dark energy a constant, unchanging presence, a dynamic force evolving over time, or something we have yet to even imagine? As we continue to study this mysterious phenomenon, we may uncover answers that not only redefine our understanding of the universe but also challenge the very foundations of physics itself. Moving forward, let us dive deeper into the incredible implications this force has on the future of the cosmos. Now turning to the remarkable legacy of Edwin Hubble, a figure whose contributions forever changed the way we view the cosmos. While Hubble is most famously credited with the discovery that the universe is expanding, his impact extends far beyond this groundbreaking revelation. Born in the late 19th century, Hubble initially pursued a career in law before his deep fascination with the stars drew him into the realm of astronomy. His determination and vision led him to the Mount Wilson Observatory in California, home to the most powerful telescope of his time. It was there, in the early 20th century, that Hubble revolutionized our understanding of the universe by identifying galaxies beyond our own and categorizing them by their shapes into elliptical, spiral, and irregular forms. This classification system remains a cornerstone of astronomy to this day, but Hubble's achievements did not stop there. He was pivotal in dismantling the long-held belief that the Milky Way was the entire universe. By observing a specific type of star known as Cepheid variables in the Andromeda galaxy, he was able to calculate distances that proved Andromeda was not a cluster within the Milky Way, but a separate galaxy altogether. This discovery transformed the cosmos from a single galaxy to an unimaginably vast expanse filled with billions of galaxies. Hubble's work also laid the groundwork for the observational techniques astronomers still use today. His meticulous observations of the relationship between a galaxy's distance and its redshift led to what we now call Hubble's Law, providing the first solid evidence of the expanding universe. In recognition of his monumental contributions, NASA honored him by naming the Hubble Space Telescope after him, a fitting tribute to a man who spent his life peering into the depths of the universe. Through his groundbreaking work and unrelenting curiosity, Edwin Hubble not only redefined the boundaries of the known universe, but also inspired generations of scientists to dream bigger and look farther. His legacy is one of exploration and discovery, and his influence continues to shape the field of astronomy to this very day. With his transformative achievements in mind, let us now explore the fascinating concept of the cosmic microwave background radiation and how it serves as a window into the universe's earliest moments. Now turning to the conclusion of our journey through these 25 astounding facts about the expanding universe, we are left in awe of the unimaginable scale, complexity, and mystery that defines our cosmos. From Edwin Hubble's groundbreaking discovery that the universe is growing to the elusive nature of dark energy and its role in driving acceleration, each fact underscores just how little we truly understand about the vast expanse beyond our tiny blue planet. We've delved into the ripples of the cosmic microwave background radiation, visited the first moments after the Big Bang, and explored the fascinating possibilities of a multiverse. We've pondered the implications of quantum fluctuations, grappled with the strange paradox that the universe isn't expanding into anything, and marveled at how gravitational waves reveal the secrets of cosmic history. These facts are not just scientific observations, they are a testament to humanity's insatiable curiosity and relentless drive to uncover the unknown. They remind us of our place in this ever-expanding universe and invite us to reflect on the profound beauty and mystery that surrounds us. What do you think lies ahead in this cosmic journey? Will we ever truly understand the universe's ultimate fate, or are we destined to forever uncover more questions than answers? Share your thoughts in the comments below and let your voice be part of this exploration. If you've enjoyed this cosmic adventure, don't forget to like the video, subscribe to our channel, and hit the notification bell to stay updated on our future dives into the wonders of the universe. Thank you for watching, and until next time, keep looking up and imagining the infinite possibilities of the cosmos.